raw data, which will be your remote sensing and these things. So how do you evaluate what your geological map actually represents at the end of your segmentation? Yeah.
I think that's where you do need some kind of ground. You need to have some idea about what is there on the ground, so that you can actually interpret the clusters you are getting to specific geology. Now that's one part. The second way of looking at it would be, I would know that which are the key inputs which are generating a specific cluster. And then if I understand that, so it could be high magnetic value, versus low magnetic value, high gravity versus low gravity. So I know that the petrophysical response of different rocks, they would have been different. So I can connect that to the petrophysical response of the rock and then interpret what the cluster actually means. Thank you very much.
And the next one.
Thank you. Good afternoon, everybody. I'm going to be presenting some stuff from one of my master's students looking at essentially geochemistry and what we might be able to pull out of it, looking at large igneous provinces, the mafic side of that, and the possible links to some mineralization. A lot of it's based on work, diagrams, plots that Julian Pierce has developed over the years, and some of the more recent stuff. So it'll be really interesting to see what Julian has to say in a couple of days' time as well. While I'll be concentrating here, taking one of the large igneous provinces that Jacob from Breugel had worked on. We did try using a machine learning type approach or a multivariate statistical approach. With geochemical data, it soon became apparent that that was just impossible. One couldn't put together data sets of any sort of size that you could do the traditional approaches to. So we reverted back to looking at spatial variations. One of the things that was one of the recent papers that Julian had was looking specifically at non-volcanic arc environments. So that took out some of the complexity and some of the confusion that might occur if you could have that. And within that, he identified effectively that for large igneous provinces, the mafic ones in particular, thinking often of plume-related situations, one has either a combination of inputs from an ocean island basalt type source, a deeper garnet controlled source, often interacting with subcontinental lithospheric mantle. And one of the things he noted in that first paper, he's working on a more detailed, a newer version of things as well, was that at least with some complexes like Norilsk, Talnak, and the Bushveld complex, the primary mineralized component of that tended to be associated with geochemical signatures that seem to be related to the subcontinental lithospheric mantle. So I'm playing games, trying to develop plate reconstruction models, etc., trying to look at the spatial patterns that we might be able to use to interpret what those models should be, but also if we've got models to start trying to predict where we might look for extensions. So this looked like a really interesting thing to try and get into, initially on some younger lips. And the one I'm going to present is the Karoo-Farrar lip. So it's about 183 million years. The possible link of mineralization in those types of mafic continental flood basalt type situations with mineralization, and whether there are any spatial patterns that one can see when one starts looking geographically, not just looking at the plots, the typical geochemical plots that mostly end up being utilized when looking at geochemistry. We have to stop. All of this work was being done with data compiled from the literature. So there's a degree of screening that one has to do. One obvious thing is to look at the immobile element side of things. We've limited it to just the mafic and basic lithologies, compared with things like the TAS diagram, which is more prone to mobility for certain of the elements. So do a match between those, and anything where the lithologies don't match, they assumed to be altered in some way as a second stage. There are limitations, obviously, that with what one's working, but we're looking at broad spatial patterns. And as you'll see, I think it actually does show something that looks to be quite useful. Very much so looking between a mantle and a crustal or lithospheric interaction component. And more particularly with this, I'm going to concentrate on using this type of diagram, the bottom right, where there's a garnet control in the magmatism and a shallower, more plagioclase related non-garnet control in the chemistry. And that's particularly picked up by the titanium ytterbium ratio. Ytterbium is not traditionally, or has not traditionally been analyzed over decades. So that's been a problem. What I've used, or what Jacob used in terms of a color scheme to illustrate some stuff, was to go to a titanium yttrium based color scheme, and it just expands the number of samples one can plot up on and show in different symbology when it comes to map reconstructions. We've concentrated with this example I'm going to illustrate on the Karoo-Farrar, Karoo being shown in yellow in terms of where the exposures are, Farrar being in blue. And this brings up one of the aspects that is a problem with GIS prospectivity, in that GIS systems don't understand that the Earth is a globe. Minus 180 is not the same as plus 180. So we're having to try and work things here. We're typically using G-place in a reconstruction environment, where if something, for instance, this little blob in here, that's the Falkland Islands, which is currently off of South America, very definitely not off of South Africa. All right. So this is a reconstruction at 183 million. We need to build that type of concept into all of our prospectivity type modeling going forward. And one of the things that Dave Evans and I, for instance, are working on is to try and create a reconstruction model going far back into the Precambrian. We're currently at around about 2,300, and we have a fairly conceptual model that will actually take us back to about 4 billion to allow one to start doing some of the tests one would like to do to then start looking at the mineralization aspects. If I just take some of those diagrams I illustrated earlier to illustrate a symbology I'm going to use. On the left-hand side was that titanium ytterbium, niobium ytterbium diagram colored by the titanium yttrium color. And effectively, if you just remember that magenta is deep garnet controlled through to blue, which is shallow, effectively plagioclase control type stuff. And then coming across onto the right-hand side, start to bring in isotope signatures, in this case, an epsilon strontium versus epsilon neodymium plot. And effectively what we're doing here is, this is just Karoo and Farrar, there's a depleted juvenile component, and effectively we color that from blue to red according to the distance away from that intersection point. So you can see it goes from blue up here through to redder and redder. And then we can also say there's obviously a wedge shape in this. So if we just take that as an axis we start with, we can calculate the angular distance of any point away from that line. And that's what controls the symbol size. So again, we can then take that and put it onto map geographic representations to look for spatial patterns which might be of interest. The diagram just at the bottom takes that same epsilon diagram, but color codes it according to the garnet control, the titanium yttrium color scheme. So you get a sense for what those are. All of this stuff out here that might be EM2 or older lithosphere effectively is showing up as a shallower signal, coming back into the subcontinental lithospheric mantle side of things. Coming across into that diagram that I referred to of Julian's, this is looking at that same diagram colored in the two different symbologies. The deeper side of things and the magentas through to the shallower in the blues up into the subcontinental lithospheric mantle sort of box. The more juvenile, interestingly, fairly depleted isotopically signature in the ocean island basalt type field up into the reds, which are the subcontinental lithospheric mantle. And if we just take, I'm just only going to use the left-hand side with it. Well, sorry, I wanted to make another point here, because a lot of folks are using isotopes and chemistry as well. We need to be aware that these different systems are often dealing with different things. And I just wanted to emphasize that by putting this in here. The rhenium osmium system is dominated by sulfides. So when you have an R factor enrichment type of thing, it's into the sulfides. It's not necessarily or generally not showing you what's in the silicate side. The right-hand side diagram here was the work we did quite a long time ago in the Bushveld complex. More recent stuff just shows the same type of thing. Looking at a model mu, think of that for a lead isotope system. Think of that as an initial ratio proxy for lead isotopes. That's the easiest way to think of it. Up the stratigraphy through the mafic part of the Bushveld complex, you can see variations from relatively low mu in the lower zone through into the main zone with a fairly higher mu, and then it happens to be fairly variable in the upper zone. Think of some of the stuff that's been presented. Think of the strontium isotopes. You have exactly the same sort of trend from fairly low strontium initial compositions, about 0.705, up to strontium isotope compositions about 0.71. But the chemistry is often telling you something different. So they're telling you different things. And then the red dots on this diagram are sulfide analyses, and the blue dots are silicate analyses, often in exactly the same rock where they've been separated. The sulfides and the silicates are showing two distinctly different lead isotope compositions because of the processes being slightly different. So back to the Karoo, using that deep to shallow sort of trend in a reconstructed sense. Effectively, the deep stuff is all concentrated into a nexus around here, with some stuff extending out in the Okavango dike swarm, failed rift. There is some stuff extending up here. Obviously, a fair amount of complexity around the Grunehonia Archean craton, bounded by Proterozoic mobile belts here. South of the Carpal craton, you have another Mesoproterozoic belt, but this subcontinental lithospheric mantle signature looks to be effectively the same geochemically, both on craton and off craton. So you're not seeing differences that you might otherwise have expected to see with that. And this big yellow star I've just put in as roughly the position where the only slight indication of mineralization occurs associated with the Karoo, and that's at Insizwa. But there are very distinct spatial patterns which are telling one something about the source and the mechanisms and the magmas that are coming in that we could theoretically start using in an exploration sense. If we say, well, we would expect mineralization to be effectively associated with the blue color scheme in this diagram. Right. And that's using, one of the other things I didn't mention with Jacob, it's really nice to have graduate students at times. Yeah, there was, when we started out, the data set had less than 40% with geographic locations. This is talking around about 3,500 analyses for the Karoo alone, let alone the other provinces that he worked on. He brought that up to well over 90% by having a lot of manual work. So take that concept, and now let's go to just using data out of the literature for Norilsk and looking at what those patterns might be there, given that we know that Norilsk has very significant mineralization. And this is the sort of pattern that one has with this pinker domain in here, picking out the extent of the Archean component of the Siberian craton. You're seeing the deep component of magmatism in samples out of the Siberian traps. Norilsk is effectively roughly where that N is, and you're starting to see that interplay to the shallower subcontinental lithospheric mantle, and possibly the interplay between the deep and the shallow. whether to what extent that's important, not necessarily that clear. The diagram at the right is not actually from Norilsk. It was just to remind you of the color scheme I was using in doing this for the Norilsk side of things. And this here is using that isotopic variation. Again, you see the same sort of pattern, very distinct geographic associations. One can go ahead and if a sample with its particular chemistry plots in one of these blocks, we can then associate it with that particular block, give it a color according to the block. And in this case, using the reds for the subcontinental lithospheric mantle versus blues for the ocean island basalt block in this diagram. And that's the plot that comes up with that. Again, very distinct geographic variations. So I'd like to just suggest that what we see in the lips, it would be really interesting to go out to more of them, more than we've done. They're distinct variations that I think could link to geochemical associations that might link on through to mineralization. I quite acknowledge that the local controls are going to be the ones that actually matter for mineralization. We're not arguing against that. We're just trying to look at what are the broad spatial district scale type stuff that might be of use. The principal mineralization does not seem to be associated with the plume centers. And to emphasize that the decoupling of both chemistry and isotopes is something that we need to take into account with whatever we do. Thanks very much.
Hello, great song, thank you. Does your work with this able to decouple between soft lithospheric mantle interaction and crustal contamination of these lips? Because it's quite common they are contaminated.
Yeah, I should probably say that up front, very anti-crustal contamination for a lot of these types of things, because if you really had crustal contamination, you're probably not going to be dealing with a mafic rock, right? And we've limited ourselves to the mafic components for any significant degree of crustal contamination. It's more likely to be a source component in many cases, to my mind, which would put it into lithospheric and the pathway through the lithosphere, rather than what I would see as actual fairly localized crustal contamination. There is a crustal component going into it, no two ways about that. And that seems to be a feature of any continental flood basalt environment, even into the Archean oceanic plateau greenstone type stuff. One's starting to see that same sort of signature from that recent paper of Steve Barnett. Not necessarily crustal, it's very clear. So I don't see it as a real crustal contamination situation.
Okay, thank you.
Now we have the last talk for the day and for the session from Michael.
So this presentation is part of the SEMACRED project, and I'm presenting the preliminary results of the regional scale prospectivity modeling, which was done for PG related layered mafic intrusions in northern Finland. Even though it's just a few names listed here, this presentation gets a lot of inputs from many other people, all involved in the consortium. So a big thank you to them all. So this is an oversimplified workflow. We saw the detailed workflow in Alok's presentation earlier. It's never linear, but just for the sake of simplicity, I've put it in a linear fashion. So we start with the conceptual modeling, where we build up a mineral systems model, taking into account all the crucial ore forming processes. And then we move on to identifying the spatial proxies or proxies that features that proxy for the crucial mineralization processes. This prospectivity modeling followed the conventional approach where the features were extracted manually. So there was spatial data processing involved, where we went through all the data sets that were available and we manually extracted all the features, which were then integrated into a integrating algorithm to get a prospectivity map. So the first step of conceptual modeling, we follow the mineral systems approach, which is based on the paradigm that mineral deposits are point expressions of lithospheric fluxes of mass and energy. So it's divided into several components, ranging from the source of ligands, energy, metal, fluids, to the transport of these different components from deep lithospheric levels to the upper crustal levels, and finally the deposition of the metal from the fluids. We use this because they are based on processes rather than analogs of known deposits. So they are more effective in predicting deposits or predicting areas which are favorable for hosting deposits, which is our aim. The new architecture of the mineral systems approach, which was again presented earlier. For now, we've based our mineral systems model on the older architecture, but we may migrate it to the newer one. So in northern Finland, we have these two mineralization episodes. The first one at 2.45 billion years ago, that's where the layered mafic intrusions were emplaced, which are of course enriched in PGEs. The second one at 2.1 billion years, which generated these conduit type ultramafic conduits, which are enriched in nickel copper. Since we're now talking about PGEs, so we'll be focusing on this episode, which generated these layered mafic intrusions. So very simple cartoon, which explains most of it. We have the magma coming up from the mantle, deep mantle, asthenospheric mantle possibly. As it rises up, the part which goes through the central portion of the craton generates these magma chambers, which form these stratification of the magma during fractional crystallization, generating these layered mafic intrusions. And the one which migrates towards the sides of the cratons generally generates these conduit type deposits. So this general transient geodynamic architecture is also very important and needs to be incorporated into our prospectivity model. So the next step of identifying spatial proxies. So we translate that's where the scale component comes into the picture. Alok talked about it in great detail. So on a regional scale, we are more effective in predicting the locations where we are most likely to find mineral deposits. So at such a scale, we have the source and pathways components, which are more important than the detailed trap components. So this is a preliminary targeting model that we have put together till now. So the source is mostly from the deep mantle, convecting mantle, or lithospheric mantle. There's a bit of a controversy for now. We believe it is the asthenospheric mantle, and there's some as part of this project itself, there's experimental work going on. Will's work might shine some light on the definite source. He's presenting a poster, I believe, and we should all check it out. The next is, of course, we are looking at ultramafic sources. So we would want to pick out anything that is rich in magnesium. So we pull out a map which generates or identifies rocks or regions where we had a lot of ultramafic activity. The mantle plume component, I'll get to it a bit later. This was not represented in the preliminary modeling. Pathways, we need to have deep plumbing architecture to pull up the magma from the deep lithospheric levels and bring it up. So we would want translithospheric faults. So for now, we've used structural maps, but in the future, we'll also be using geophysical data sets to identify structural discontinuities. And as I mentioned earlier in the cartoon, where if the magma goes through the craton, it forms these layered mafic intrusions. So we would want to look at the paleocraton margins. So anything away or close to the margins would be favorable for nickel sulfides, but further away from them towards the craton centers would be favorable for layered mafic intrusions. Among the traps, we look at higher order faults, cross-cutting faults, which form these structural faults, structural traps. And that is where we've used a structural density map. In this simplified cartoon, we also see that there's clear stratification ranging from ultramafic to mafic. Generally, the PGE mineralization is between the mafic and ultramafic contacts. So we have also tried to generate a layer which tries to map this stratification. So neighboring ultramafic to mafic lithologies. And of course, since these are ultramafic rocks, they're very dense. They have a clear anomaly in gravity data sets, also in magnetics. So we have layers of gravity and magnetics. And the common enrichment, nickel, chromium, vanadium, and PGEs in the layered mafic intrusion. So we have geochemical layers representing each of those elements. So the next step is where once we have this model, we know what we need to look for. Now, the next step is to map those critical processes in the data sets that we have available. This is where the manual feature extraction comes in using GIS. So some of the criteria which was mentioned earlier. So paleocraton margins, for now, we have just relied on literature. We pulled out these maps from Wolfgang Meyer's and Holta's papers, loosely digitized them in GIS itself and use them. But in the future, we are trying to look for other proxies. Christopher Adegbe is presenting a poster. He's working with hafnium neodymium isotopes, which are giving some indication on the crustal architecture, the spatial variation of these isotopes. So we might want to look into that and use those variations to build these craton margins. So based on those proxies, we have a layer defining the craton boundaries, which was manually digitized. So this can be improved in the future. From the geology, we had extracted these lithologies, which are neighboring from ultramafic to mafic. So the neighborhood association trying to represent the stratification. From rock geochemistry, we had these individual layers for copper, platinum, chromium, and nickel, which went into the trap components, and the magnesium ratios to represent the high magnesium sources. From geology, we also extracted ultramafic lithologies, of course, and distance to dikes. The intention behind dikes was to map the feeder dikes to the layered mafic intrusions. And from structural data, we got out larger faults, implying deeper faults, so distance to those faults, which would act as pathways, and shorter faults, which would mean that they are higher order, smaller faults, near the crust. So we mapped out the densities of these faults for the trap component. For this preliminary modeling, we have not used processed geophysical data sets. They were just the magnetic anomalies and Breugel gravities were just fed in as they were, but this would be worked on as well. Some unused data sets which needs to be worked on. Again, regional geochemistry we plan to use in the future, but I don't think we'll be using stream geochemistry because the coverage is inconsistent. And integrating into a fuzzy inference system. So something about fuzzy inference system and the reason why we chose to use it. Largely, it has been already covered in Alok's presentation. It works and fuzzy inference systems allows us as geologists to replicate our thinking and reasoning, a geologist's reasoning into the computer. So it's quite easy for a geologist to understand and reason. And therefore, we chose to start with this integrating model. So based on the mineral systems model, we had 3 fuzzy inference systems for sources, pathways, and traps. The outputs of each of these fuzzy inference systems was then combined using a fuzzy product operator to get the prospectivity map. So the circles in green are the layered mafic intrusions. The circles in gray are the layered mafic intrusions. And the green squares are conduit type deposits. The preliminary result captures quite most of the layered mafic intrusions along this belt, but we also find a high prospective zone here, which is under this Paleoproterozoic metasedimentary horizon. So this can indicate there are several undiscovered layered mafic intrusions buried under the metasedimentary horizon. We also have some high prospective zones identified here in the north. So as I mentioned, it's a preliminary result. So we'll be working on this to refine this further. So starting with geophysics, which was not processed at all, we'll be using derivatives of the geophysical data. The geology and the structures were used as they were, but we clearly have 2 different mineralization episodes. So we would be filtering all these data sets as per ages. So only the ones related to the 2.45 episode would be used in this modeling. And of course, the geochemical data sets. Something about plume center, since that drives the system. We need to reconstruct the paleogeography to understand where it was, what the geography was, and how, where the plume acted. But we're talking about 2.45 billion years ago. It brings in a lot of uncertainty. It's quite difficult to understand that. So one way would be to follow these radial dikes and try to locate the plume center. Something under discussions, we might use it. And another thing about MOHO that we have used, this was supported by Catherine Booth's numerical modeling. They identified that the magma on its way up forms these plumes of magma. And we see evidence of that in northern Finland from tomography surveys. We have what the geophysicists call high velocity lava crusts. So they are mafic bodies deep around the MOHO boundary. And it's empirical knowledge that wherever we have such high velocity lava crusts in northern Finland, that's where we have most of the layered mafic intrusions. So this might support what the numerical modeling is already showing us. So next, we might want to map these horizons and use that as a crustal architecture component in our prospectivity modeling. So thank you for now, and hopefully we'll have better results in the future.
Don't forget to get a poster session with your drink. And those people who have their posters for today's sessions, remember to talk tomorrow, we have new sessions. We need the space for tomorrow's posters. So after the poster session or tomorrow morning at the latest.